the simple AC circuit containing a power supply and a resistor only. This is like slide 3 on my PowerPoints that I gave you. Okay, now the main difference here looks just like we saw before. The schematic representing the power supply is different. If I go over to my palette here, here's the original battery I used in a DC circuit. When the current flows in only one direction, what I'm moving my cursor over is what I would have used. Now I'm using this thing down here, which appears like this, and notice it kind of looks like a wave pattern representing the alternation of current, which is going to occur for this battery. Now, right now I have the voltage set at 12 volts, and I have the frequency set at 0.5 hertz. Now, what does that mean? Every second, 1/2 of a wave of variation of the voltage from max to min will occur every second. 1/2 of a wave varies each second. Now, if I want to see that behavior, look over here. I have a chart which is showing right now nothing because I don't have it attached, and actually nothing because I'm not playing anything. But let me put it on here, and I don't think it's going to show anything when I put it on here because, again, I'm not hitting play. But now let me hit play, and here's what you're going to see as I'm showing the behavior of the voltage. Now notice I go from 504 to 505 seconds. Down here I'm showing the time, and it's moving very quickly, so it's kind of hard to see. But what you should recognize from my picture is, I can move my cursor over here, I have a variation between Vmax and Vmin. Vmax and Vmin. And this has a frequency of variation so that 1/2 wave of variation. Now, a whole wave starts at 0, goes up, comes down, goes minimum, and back to 0. That's one wavelength. So 1/2 wavelength is passing by each second. So that's how much voltage we have varying. Notice I have the voltage set at 12, and it's hard to see a little bit. Here's 10 on the scale. It's going from a Vmax of +10 down to a Vmin, scratch that, sorry. It's going from a Vmax of +12 down to a Vmin of -12, and it's varying between that for a rate such that it's 0.5 hertz of occurrence. Now, right now, even if I put the current meter on, or the current chart on here, notice I'm getting no current. Well, the reason I'm getting no current is because, and also my ammeter, which I put in the circuit, is reading no current either. Well, that's because I have a switch on the circuit. The switch is open. The power supply is currently delivering that voltage, but since the circuit is not complete, the current is not flowing through the circuit. So if I come over here and I grab and I close, now we get some action between the current and the voltage on the circuit. Now you'll notice that now the current is varying from a maximum to a minimum, just like the voltage is varying from a maximum to a minimum. Now what we can actually do is see if Ohm's law is verified. Let me turn this off arbitrarily, and you will note actually if I put the voltmeter on down here, I'm at a voltage of a minus 11.99 volts. And remember, the resistor is a 10 ohm resistor. Minus 11.99 divided by 10 is negative 1.2 amps. And that's what you see on the display. Now, if I go to my charts, notice my voltage chart right at the origin is at right now minus 12. I mean, it's really a little bit below the 10. And it's hard to see here, again, because it's not really scaled to read very efficiently. But the current reading at the origin, this is my current scale, at the origin I'm at minus 1.2 when I'm at minus 12 volts. Now let me just let it run a little bit arbitrarily again. Now I'm at positive 9.7 for the voltage, and you'll notice that's up here now at the origin, and I have a current, not surprisingly, because V over R equals I, and R is 10, so I divide the voltage by 10, and I'm getting positive 0.97 amps. And if I come over here and look at the origin, the time 0 point on my current scale, I also see that it is at the same time, I'm sorry, that the current is at that same point as well. Now, another interesting thing I want to point out to you is that the resistors in AC circuits don't care. What we're essentially saying is the current is flowing left and then right through that resistor. The resistor is independent of whether the current is moving right to left through it or left to right through it. It drops the same potential no matter which way the current flows. So in other words, when we screw a light bulb into an AC circuit, it doesn't only light up when the light is going in one, and when the current is going in one direction through it. It lights up no matter which way the current goes through the light bulb. So it doesn't matter which way the current is going into this, it will have the same drop of potential from one side to the other. Now, another thing I think I'm going to do here is I'm going to change the frequency. Right now, the frequency, as I said, is on 1/2 hertz. Let me come over here and hit 1.5. I didn't hit 1.5. I hit 1.5 hertz. I better enter that to make sure I do it. Now when I hit play, let's look at what happens to the voltage and the current. Now notice the voltage and the current have changed their pattern dramatically. The length of a complete cycle has gotten way smaller because now 1.5 times in a second a complete change of the voltage and change of the current has occurred. Now notice though again, if I arbitrarily stop, I stopped where I'm at a 10.515 voltage reading and V equals IR, so if I divide that by 10, I'd get a 1.05 amp reading. And now notice, if I come over to my chart, I look at my origin, my time 0 of the voltage curve, I'm right at 10.5 volts. I come down to this one, I'm at, it's hard again to see because the markings are not telling me, but believe me, it's at plus 1.05 amp. Now again, I'm just going to arbitrarily let it run and then let it stop. Now when I'm at 9, or notice this is negative 9.24 volts, I'm at negative 0.92 amps. So if I come over to my origin, I'm going to be right at negative 9.2 volts. I come to this, I'm at negative 0.92 amps. Now, one last thing I want to say about this before we move on is that I want you to notice that the current and voltage are what we call in phase. When the current hits a peak, the voltage hits a peak. Now, I can show you that by stepping this. Notice I'm stepping it point by point by point till I get the voltage to a peak of 12. I didn't quite get there. It's as close as I'm going to be able to get. My current is now at a peak of 12. My voltage is at a peak of 12, of 1.2. Now, if I step past that, and you can notice the things are changing, let me go to the bottom. Now I'm at negative 12. Essentially, I'm never going to get to exactly negative 12. Notice that the current reading right up here is negative 1.2. When I'm at the bottom of the voltage peak here, I'm at the bottom of the current peak here. When I'm at the top, and let me just step a couple more. When I'm at the top of the voltage peak, I'm at the top of the current peak. So what we say, and I want you to remember these words, that in an AC circuit, the current and voltage for a resistor are in phase. Okay, so let's move on and just look at a couple characteristics of series and parallel resistors. What I've done is I've placed two 10-ohm resistors in series in the AC circuit. Again, This is discussed on slide number 3 of my PowerPoints I supplied. Nothing different will occur here than what occurred for the DC circuit. I still have, as you can see, my voltage set at 12 volts, but now I have a 10 ohm resistor and a 10 ohm resistor in series. 10 ohms plus 10 ohms is really 20 ohms. So this should be a 12 volt current divided by 20 ohms. That sounds like a 0.6 amp output current that I should get from those two characteristics. Now I don't know that yet because I got this thing turned off. Let's take a look at letting it run a little bit. Now let's come over here to my chart. Notice that my peak to peak is plus 12 to minus 12 on the voltage, but now my peak to peak on the current is something below 1 to something less or a little bit more, we should say, than negative 1. So my current characteristics compared to my voltage characteristics have changed dramatically. Why don't we arbitrarily stop and pick out one of these points? I'm claiming that when the the voltage is at a negative 2.248 value, I'm getting a current of negative 0.11 amps. And I have my calculator in my hand. If I take 2.248 and I divide by 20, guess what I get? I get 0.11 for the current. So Ohm's law for series resistors is holding in this particular case. And if I come over to my chart, again, I look at my voltage chart, I'm at negative, it's hard to read again, when this is at negative 2.248 volts, I come to my current chart, I'm at negative 0.11 on the amps at the origin of that curve. Now let me just let it play again arbitrarily and just grab one. When I'm at 6.745 volts, and you can see that's be this point here, I have a current of positive 0.34 amps, and if I take 6.745 divided by 20, I would get 0.34 amps. Now the other thing you should notice, of course, is as we've talked about in direct current circuits, this resistor is dropping half the voltage, the resistor on the left is dropping 3.372, and the resistor on the right is dropping 3.372 at that time. And if you add those together, you will get the total voltage dropped by the series resistors of 6.745 volts. Now again, if I were to arbitrarily, and let's maybe start the clock here, and let's just come up here and for fun, let's make the frequency up to 2.0 hertz, and I hit done. Notice how dramatically now the change in voltage and current are occurring. And you can see on my voltmeter and current meter, it's really crazy. That's why a real AC voltmeter doesn't do this. We report RMS voltage, which maybe I'll say something about in our next meeting. You report RMS values, and I'll just save it till then, till when we do that. But you will notice, let me again stop them, that the voltage and current again are step by step in phase. And what do I mean by in phase? Right now I have a negative that's not really showing the same thing. Maybe that would be because I have this backwards, but I don't think I have that backwards. Let me let it run a little bit more and let me stop them. But notice that when I'm at about 7.05 volts on the voltage scale, it's really hard to see. If I divide that by 7, I would get 0.35 on the ammeter scale. And so everything still works. And again, notice I'm going to be dropping half the voltage across that resistor and half the voltage across this particular resistor. Okay, so now let's look at some parallel cases. Now what I've done is set up an AC parallel resistor circuit. I have it turned off right now. Nothing is happening. I have the circuit switch closed. You can see if I put my voltmeter across the voltage, to read the voltage drop across the parallel resistors, I'm getting 7.052 volts. Now, let's verify that Ohm's law works. I have two 10 ohm resistors. Of course, the equivalent capacitance, equivalent resistance is 1 over 10 plus 1 over 10 equals 1 over Req. That's 2 over 10 equals 1 over Req. That's Req equals 5. So this is like a single 5 ohm resistor in place of these two parallel 10 ohm resistors. So what would I expect then if I have a voltage of negative 7.052, and if I divide 7.052 divided by 5, I'm going to get a value of 1.41 amps, exactly what I see. So Ohm's law holds for parallel resistors in AC circuitry, just like it holds for DC circuitry. Now I'm going to start running the circuit so you can see the time characteristics between the current and the voltage. Now the top one is the voltage. It's varying between plus 12 and minus 12 volts. The bottom one is the current. It's varying between about plus 2 and about negative 2, a little bit more actually, plus 2 and negative 2 amps. It's a little bit more depending. Of course, again, the resolution is not the greatest. I can't really tell. Again, I arbitrarily stop it when I'm at negative 5.78 volts. And again, we can see that on up here, I hope. When I'm at my negative 5.78 volts, I'm at negative 1.16 amps. So, of course, what we're saying is 5.78 divided by 5 is negative 1.16. And again, let me just arbitrarily run it. When I'm at positive 11.974 volts, if I divide that by 5, that would be 2.39 amps of current that would be flowing in that particular case. One more time, just to point out, if I look at the peak values of current and voltage in the AC circuit, I would note that they are in phase. When the voltage reaches a maximum, the current reaches a maximum. When the voltage reaches a minimum, the current reaches a minimum, and it continues through the entire cycle. So I've changed the setup. I have gone to a capacitor circuit in an alternating current situation. Now, let's first remind ourselves about a direct current circuit containing capacitor. If it would be direct current, what you would notice is that immediately when you close the switch, the capacitor charges fully, and that keeps charge from flowing through it anymore, and the current stops flowing. It just charges the capacitor holds that charge, and that impedes the flow of current in the circuit. Current falls to 0 instantly. Now what we can see here, and I don't have this playing yet, so let me start it playing. You can see that as time progresses, I have my alternating voltage on the top scale above. Now I've had to slow the frequency down quite substantially in order to get this to operate correctly. As a matter of fact, we can go over those characteristics. The AC voltage I've bumped up dramatically as well. I'm at 100 volts for my AC voltage, and that's going, as you can see up here, from a peak of 100 max down to a minimum of minus 100. That's what we mean when we have 100 volts. That's the peak-to-peak voltage being set. That's what we call that. That's the peak-to-peak voltage, and it varies from all values in between plus 100 and minus 100 very periodically. And the period, if you like, well, actually the frequency is 0.2 hertz. The period is 1 over the frequency. So 1 divided by 0.2 would be 5. Every 5 seconds, there's one complete loop of the voltage. So if I go from this point up, down, 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 and back to that same starting point. That will take 5 seconds for that voltage to vary in that. Again, if you'd like me to say that one more time, the period, the time it takes to complete one loop is 1 over the frequency. The frequency counts how many waves there are per second. The period says how long it does to do one wave. They're the inverse of one another. So the frequency in hertz of this particular circuit is 0.2 hertz. The capacitor, as you can see down here, has a rating of 0.05 farads, and as I said, the voltage is at 100 volts. Now you'll notice I've gotten rid of the voltmeter and the ammeter. That's because there are now very weird characteristics between the voltage of the circuit and the current of the circuit. They are no longer in phase. I talked a lot about the in-phase nature of the current and voltage when you have resistors in circuits. Now the current and voltage are out of phase. First of all, let's notice, again, I want to point out, it's weird simply because of the fact that there is a flowing current. Now notice, the current is on this bottom scale. It's varying between about +7 and -7, roughly. And that's +7 amps to -7 amps as the voltage goes from +100 to -100. One of the first things to note, though, is that the current does constantly flow. If you want a little bit of a discussion about that, maybe you can refer to the slides. This capacitor is charging and discharging constantly during the alternating current. But it depends on how fast the alternating current is varying as to whether or not the capacitor gets a full charge or not. If the frequency is really, really slow, then the capacitor has a full time to charge. It can charge completely, and then the current can't flow anymore. But if the frequency of the alternating current is fast enough, the voltage is varying fast enough, then the capacitor doesn't have time to charge. And it only partially blocks the current from flowing, so it acts partially like a resistor. Now there's a magic formula for this so-called capacitive reactance, the amount of resistance supplied by the capacitor. It is 1 divided by 2 divided by pi divided by the frequency divided by the capacitance, and that gives you the resistance of the capacitor in ohms. Again, look at my slides for further discussion of that. So if the current if the voltage has a sufficient frequency, then the capacitor doesn't have time to charge completely, and it simply acts like a resistor in the circuit. So there's a constant flowing current in the circuit that now I do want you to note, it's not in phase with the voltage. Here's what I mean. I'm stopping it there, and notice my voltage is about at -100. But meanwhile, my current is past the minimum current. As a matter of fact, let me step it just a tad bit further here. Now I'm going to claim I'm exactly at -100 volts. Take a look on the scale. I'm at exactly -100 volts. Now look at the current reading. The current reading is at 0 amps. So that's a very weird behavior. Unlike when you have a resistor, the capacitor voltage and current are not in phase. As a matter of fact, the current is what we call ahead of the voltage. The current leads the voltage. The current is already at 0 while the voltage is still at -100. Now, if you were to measure that distance in terms of a wavelength, that is 1/4 of a wave. And if we think of the cycle of a wave as going from 0 to 360 degrees all the way around one time for each wave, then 1/4 of a wave is what we call 90 degrees. So in conclusion, the capacitor is 90 degrees out of phase for its current compared to its voltage. We say that the current of the capacitor leads the voltage by 90 degrees. That's how it is described by electronics engineers. The current leads the voltage by 90 degrees. Now, again, let me step this forward a little bit. Let me go to when the current is at a max. Notice when the current is at its maximum value, then the voltage is right at 0. So once again, that's a quarter of a wave out of phase. 90 degrees ahead, the current has already reached its max while the voltage is at its value of 0. So this is why I don't have the ammeter and the voltmeter on this circuit anymore. They're not built into this program to read proper AC values that I'll again talk about in our next lab. But what we can do is still calculate the relationships between the peak current and the peak voltage. The maximum of the voltage, as we can see on the top chart, goes from plus 100 to minus 100. The maximum on the current, as we can see below that, is somewhere above 5 amps to somewhere below negative 5 amps. Now, if I want to find that value exactly, I would have to calculate the capacitive reactance of this circuit. The capacitive reactance of this circuit can be calculated by taking 1 divided by 2 divided by F, and the F value is 0.2, and divided by C, and the C value is 0.05. If you do that, you will get the so-called resistance of this circuit. If you divide the peak voltage by that resistance, you will get the peak current. And if you took the negative of that and divided that into the voltage, you'd get the negative peak current. So that will be something you'll be doing for your laboratory report. Okay, so let's now then conclude by looking a little bit at putting a solenoid in a circuit. Now our final circuit will be a circuit, an AC circuit, which contains a solenoid, or as we call it here, an inductor. Now, this goes by 3 names. It's either a coil, an inductor, or a solenoid. It's very simple. It's not mechanical at all. It's just coils of conducting wire. As we talked about in the Faraday lab last week, these conducting loops carry current, and then they generate a magnetic field internal to them. Well, this magnetic field that flows through the loops makes a Lenz's law problem where it has to generate an opposing current to stop this from occurring. So an inductor in a circuit, as current attempts to flow through it, changes magnetic flux in the loops. The loops react to oppose that change in flux and make what we call a back current, which makes them have a resistance associated with them. Now the symbol for the coil, as you can see over here on the palette, is this coily looking thing. It's either just a coil of conducting loops. Sometimes you put a core in it to make it act much more powerfully. And the unit that of strength of this as a Lenz law opposing field maker is called inductance. The unit of inductance is known as the Henry, and right now the coil that I put in this circuit is set at 10 henries. You can look on my slides for a little more about the units that are used. Essentially what this is going to measure is the pushback of the coil. When current flows in it, it changes the flux in the loops. The loops don't like that change in flux, so they create their own current to push back against that. And this makes the coil act like a resistor in an AC circuit. A coil will not act like a resistor in a DC circuit. It'll do it for a fraction of a second while the current initially begins to flow, but once the current is steady in the direct current circuit, then the flux doesn't change through the loops, so now the inductor no longer provides any resistance at all. Only in an AC circuit where the current is constantly reversing do you have a constant change in flux of the coil loops, so that you have a constant change in back current, pushback resistance provided as it tries to oppose the change in flux that it experiences as current flows through the coil. All right, so that's the basic idea of what's going on. Again, the circuit has an AC voltage, as you can see in the upper right-hand corner, of 100 volts. It has an AC frequency of 0.5 volts. And again, if you take 1 over 0.5, that would say that there are 2 waves every second. So meaning that the voltage goes from max to min to max to min 2 times every second, because the frequency is 1 over the period of the wave, if you like. Now I have the wave, the circuit stopped right now. Let me hit the play button, and you can see now again my graphs are running, showing the voltage and the current. Why, again, I can't use meters here is because, again, there's a phase relationship difference between the current and the voltage when there's an inductor in the circuit, unlike when you put a resistor. When a resistor is in the circuit, when the resistor is in the circuit, the voltage and current are exactly in phase. When the voltage hits a peak, the current hits a peak. When the voltage hits 0, the current hits 0. Here, there's a phase difference, as we saw for the capacitor in the particular characteristics of behavior of this circuit as well. We can see that the current, let's start with the voltage up here at the top. It's going from plus 100 down to minus 100 sinusoidally as it varies with time. Simultaneously, the current is going from something around 3 to something around negative 3. So I got about positive 3 amps to negative 3 amps as the voltage goes from plus 100 down to minus 100. Now, one of the things you're going to have to do is calculate what we would predict that the current would be in this circuit by calculating the so-called inductive reactance. The inductive reactance is, there's a formula on the slides. It turns out to be that the resistance is 2 times pi times the frequency of the AC voltage times the inductance in henries of the particular inductor that you hooked in there. If you multiply that together, you get the behavior of the resistance of this device in the circuit. And if you divide that resistance into the voltage, you should get the value of the current that we're seeing flowing through this circuit. So that's one of the things you're going to be doing for your lab report. What I do want to show, though, is a close, careful assessment of the phase relationship between the voltage and current in this particular circuit. So I have stopped the voltage at its max. The voltage, as you can see in the top graph, is at plus 100. While the voltage is at plus 100, the inductance is behind that. Okay, the inductance is at 0. Not the inductance, sorry. The current is reading 0 when the voltage has reached 100. Okay, so in this particular case, again, there's a phase difference between the two. In this particular case, the phase of the current is behind the phase of the voltage. And again, it's 1/4 of a wave. When the voltage is at peak, the current is at 0. It's trailing the voltage because its peak has already passed. So what an electronics engineer would say is that in an AC circuit with a coil involved, that the current trails the voltage. And by what measure does it trail the voltage? 1/4 of a wave, which if you relate a wave to 360 degrees, that would be 90 degrees. So a coil current trails the voltage by 90 degrees. If you were an electronics engineer, that would be something that you would be very familiar with as you design complex circuits, which can do very interesting things to make our lives so well, work so well based on the values of these components and their behavior in a circuit. So I'm going to have you calculate the value of this inductance of the particular setup we have here, and then you can use that to do an evaluation of what you would predict the current would be. And it should be, as we can see, somewhere around +3 and somewhere down to a -3, something like that when you do the calculation.